Все, вроде бы пошло. Все, Саш, можете...
Okay. Okay, my talk will be about homology of Torelli group, and I start with a definition of this group and well, with general explanation of what is this science about. So if we have an compact oriented surface of genus G, compact oriented surface without boundary, then we can consider the mapping class group of this surface. This is we take the group of orientation preserving homeomorphisms of this surface onto itself and factorize it, take the quotient of it by the connected component of unity. We get just group without topology, discrete group, and this is called mapping class group. In a sense, this is an Arbifold fundamental group, Arbifold by one of the modular space of curves of genus G curves. Exactly, this means that modular space is the Teichmüller space quotient by this mapping class group, and Teichmüller space is just topologically just as Euclidean space, homeomorphic to Euclidean space, to an open ball of dimension 6g minus 6. And so if this action was free, then we get exactly the Eilenberg-MacLane space for the mapping class group. This action is not free, but it is almost free. It has finite stabilizers. All points have finite stabilizers. So in some orbifold sense, this is exactly the fundamental group of what we get. Okay, but there are many things which are known about homology of and cohomology of mapping class group. In fact, since up to finite stabilizers, this is something like Eilenberg-MacLane space, then we have that with rational coefficients, the cohomology of the modular space is exactly the cohomology of this mapping class group. This is not true with integral coefficients or with other coefficients, but when we speak about rational coefficients, then this is exactly the same. And there are plenty of things which are known about it. There is Madsen-Weiss theorem, which says that when genus goes to infinity with rational coefficients, in stable genus, we have only polynomial ring in Miller, Mumford, Morita classes. We have other things, especially concerning topological rings in this and so on. I don't want to speak about it since I'm not a specialist. And in fact, what I want to say that this mapping class group contains a very natural subgroup. We can take just the kernel of the natural homomorphism from the mapping class group to, not from modular space, but from the mapping class group to the symplectic group. this homomorphism goes from the action of the mapping class group on the homology of the surface. This action preserves intersection form, so it is exactly, its image lies in symplectic matrices, and this is called Torelli group. And much fewer is known about its homology. For mapping class group, there are still a lot of things which we do not know, but for Torelli groups, we know very few. And my talk will be about this group and about problems around it. Okay, first of all, if we take the Teichmüller space and factorize and take the quotient of it, not but the whole modular, not by the whole mapping class group, but by Torelli group. Then what we get is called Torelli space, and it also has very natural interpretation. We can say that it is a modular space of genus G curves with a symplectic basis in first homology. And in fact, when, for instance, we consider a period map, we take holomorphic differentials and take their periods, we need to have to fix some symplectic basis, A cycles and B cycles. And so Torelli space is exactly those space from which this period map goes. It goes to Ziegel upper half space, and it's exactly from this Torelli space. This is Ziegel half space. Okay, so and here, unlike if for the mapping class group we had finite stabilizers, here we have free action. It is known that this Torelli group is torsion free, and hence it acts freely on the Teichmüller space. And because of that, this Torelli space is exactly the Eilenberg-MacLean space for the Torelli group. And so homology or cohomology of Torelli group with any coefficients is exactly the same as homology or cohomology of this Torelli space with the same coefficients. So now not only with rational but for arbitrary coefficients, and all the topology of Torelli space, okay, it sits in some sense on this Torelli group since it's just an Eilenberg-MacLean space. Okay, I start with several.
Sasha.
Yeah.
Whether the Torelli space possesses nice compactifications similar to that of moduli spaces, like Deligne-Mark factor?
It seems not. That I don't know any good compactification, and I think there is no of them. It is something which is okay. It's something very intermediate between Teichmüller space and maybe and modular space, and I do not think that it is that some good compactification should exist.
Okay, thanks.
Maybe okay. Natural compactifications of Teichmüller space and of modular space are completely of different nature.
Excuse me, but if we
consider the Torelli space as a bundle, no, not locally free, maybe some bundle over the modular space, then compactify the modular space. Can this bundle be extended to the compact modular space?
Can the bundle be extended to compact modular space?
But the homology group drops there.
What does it do? What do you mean drops?
Because homology of a singular curve is less than homology of a smooth curve.
Yes, yes. At least no natural way to do it. Maybe it can in some strange sense, but at least
maybe it loses this interpretation in terms of kernel of some map.
Okay, at least I never seen such.
Okay.
Thing.
Thank you.
So I think the answer is no, but at least I don't know.
One remark, sorry, whether Ziegel is written starting with S rather than with Z.
Oh, I'm sorry. Yes, sure. But I don't. I think
it was another Ziegel.
It is another Ziegel. I don't know. I'm sorry. Okay.
No, if he was written with Z, that'd be Ziegel in German, but he is Ziegel with S. No, it's
right.
S.
Right. S. Okay.
S, yeah.
Okay, I'm sorry. Okay, first of all, if we take genus 1, then everything is very trivial, since the mapping class group is just SL to Z, and so the Torelli group is trivial. And also, I would like to notice there were several very nice results by Johnson in 1980s, and I recall some of them. First of all, he completely he proved that EG is finitely generated, provided that G is greater than or equal to 3. Starting from genus 3, it is finitely generated. And also he computed the first homology group of it. This is just means that this is just abelianization of the group, so the quotient by commutator subgroup. Okay, I write his computation in the following way. It has free part and it has two torsion, but which is even more important, that he computed this as module of symplectic group. I don't want to stop on this result in more detail, but it described explicitly the action. So first homology group is known, and actually it is the only homology group which is known exactly up to now. Okay, but now I would like to return to this situation. We have Torelli space, and we have period map to Ziegel upper half space, and if genus is 2 or 3, this picture gives many important things about cohomology of Torelli group. Indeed, first of all, let us start with genus 2. If genus is equal to 2, then it is known that this mapping is 1-to-1 onto some onto some open subset in this Siegel upper half space. So the picture is like that. First of all, this Z2 is topologically just R6. And we have here, if we add stable curves, if we add curves which are like that, then this period mapping would be onto. But if not, then we have here loci of period matrices for such singular curves. Each of these loci is topologically R4, and we have this situation. We have R6, and we have several R4s, infinitely many, in fact, which are removed from it. And in fact, one can prove that the Torelli space, and it was proved by Mess in 1992, that the Torelli space is homotopy equivalent to, I'm sorry, I forget English word for this bouquet of infinitely many circles, and the Torelli group is just the free group with infinitely many generators, infinitely generated free group. So, okay, this is the only case when we know this group exactly. And in fact, we also know that this group is generated by certain loops that goes once around this one of those R4s, and because of that, this Torelli group is generated by the following. Its free generators are certain then twists about certain separating curves that separate each separating curve separates the homology of splits the homology of the surface into into the orthogonal sum of two rank 2 moduli, and okay, in fact, each of those R4s corresponds to different splittings. So those R4s correspond to different splittings of the homology of S2. And for each splitting, we have one generator. So for genus 2, the picture is rather simple, but unlike while for genus 3 and higher, we have finitely generated group, for genus 2, it is not finitely generated, it is free infinitely generated group. Okay, and also we can consider a similar picture for G equal 3. If G equal 3, then the Siegel up half space has real dimension 12. It is topologically R12. But here the situation is more difficult, namely this mapping is 2 to 1. And it is, we have here some hyperelliptic loci. In fact, several of them, since we have several possible hyperelliptic involutions. These hyperelliptic this is locus of period matrices of hyperelliptic curves, and it is 2 to 1 branched along this locus. But also we have again loci of period matrices of singular curves, and singular curves here are like that. We have genus 2 curve here and one, so it corresponds to splitting of the homology of surface of genus 3 into one rank 4 summoned and another rank 2 summoned. And okay, it is easy to compute that real dimension here is 8. Real dimension of hyperelliptic loci is 10. And it is also possible these red submanifolds that correspond to singular curves, they have triple intersections which correspond to splittings of the form V1 plus V2 plus V3. And we have exactly 3 such 8-dimensional submanifolds that meet here, since we can group two of these in 3 ways. And these intersections have dimension 6. And so the picture is like that. So the picture is more complicated, but still some information, so we can compute Torelli group.
Sasha, may I ask you?
Yeah.
In your description, the generation to stable curves of compact type appear all the time. Are these irreducible curves with nodes appear in this picture, or everything goes smooth across this divisor? So when you pinch not the separating cycle, but some...
Yes, when I pinch not separating cycle, but
what happens with then period map, of course, goes to infinity.
Yes, periods go to infinity. So I'm not interested in these degenerations. I'm interested to those things which are removed from the Ziegler upper half space.
Okay.
So they are not interested in this particular question. Yes, and in fact, from this viewpoint, first of all, this picture was studied first by Johnson and Milson in 1992, and they managed to prove that the third homology group of Torelli group of genus 3.
Sasha, can you move a little bit up this?
Yeah. Okay. One moment. Sorry. Okay, they proved that this group is not finitely generated. This was the first, they considered those picture and found out this result. In fact, there more or less there are infinitely many cycles that go around these 8-dimensional submanifolds. This is the main idea of the proof. But then Richard Hayne in 2004, he studied this in more details. In fact, in this situation, starting from genus 3, we have the following splitting. If we consider coefficients when 2 is invertible, For instance, we take homology with coefficients in z over with 1/2 added, or even rational homology or so on. Then we have splitting of this homology plus and minus, where plus and minus denote eigenspaces for the action of hyperelliptic involution. We have hyperelliptic involution on this, not hyperelliptic involution, okay, the involution which changes these, the involution on Torelli space induced by hyperelliptic involution. It changes these two leaves of this covering, and we can consider those homology classes which are invariant under this action, and those which are skew-symmetric under this action. So we get this decomposition, this splitting, and in fact, Hein shows that okay, this picture is good for studying this plus summand, since for it we just can go to the homology of we can just forget about this ramification and just take homology of this R12 with those red surfaces deleted, and this is just the same as this plus component of homology of Torelli group, and Hein computed it explicitly.
Is it correct that you have infinitely many such red manifolds?
Yes. I just cannot. Yes, I'm sorry. As in this situation, we have infinitely many these red submanifolds. They intersect in some difficult. Some triples of them intersect, and this combinatorics is rather hard. So this is not so easy. But still, Hein managed to compute explicitly this summand, and which is more interesting, the result is as follows. Okay, H1, the first homology is not interesting since it was computed before. The result is as follows. If we consider H2 and consider this plus component, then it's just 0. And if we consider H3 and H4, then either of them is not finitely generated, and he described them explicitly as modules over SP6. So explicit answer is known, but only for this positive part, not for negative one. Okay. Well, and in fact, I should mention it before, but if we go in historical order, then it was later, but I would like to mention it now, that Bestvina books and Margalit in 2007, they proved that the homological dimension of the Torelli group is 3G minus 5. So we have no homology above this bound, and so for genus 3 it is exactly, we have no homology upper than 4. Okay, but still, first of all, even for genus 3, this picture says nothing, almost nothing about this negative part of homology, antisymmetric part of homology. And second, if genus increases, then we cannot apply the same technique, since instead of okay, the image is not an open subset of the upper Siegel half space, it becomes a difficult, a complicated submanifold. This is famous Riemann-Schottky problem, and okay, it is much more difficult to work with this. Okay, so what is known about and what is not known about homology of Torelli groups? Okay, as I have already now some list of results. As I have already mentioned, E2 is infinitely generated free, so we know everything. For E3, we know that first of all, for all EG, we know that the first homology is computed, as I have already mentioned. But for E3, we know that both E3 and E4 are not finitely generated. Also, for all G, we know that this homological dimension is 3G minus 5. And also, we know the following. First of all, first of all, Bestvina books Margalit, when they proved that the homological dimension is 3G minus 5, they also proved that the top homology group is not finitely generated. So in genus 3, this just recovers the result by Hein, but in high genera this was new. And also my result of 2018 is that for any k between 2G minus 3 and 3G minus 5, this group is not finitely generated. Okay, we cannot compute these groups explicitly, but at least first natural question is which of them are finitely generated and which are not. Namely, from which dimension the infinite topology of Torelli groups starts. So it's a natural question. If we have this Rayleigh space, then okay, we can ask whether it is homotopy equivalent to a finite CW complex. The answer is not, since it has infinitely generated homology. But okay, can we find a homotopy equivalence to some CW complex with finite some M skeleton? And for which M we can find this? So it is always possible to find it with finite M one skeleton, but until now it is not known even about finite two skeleton. And this is actually one of the most interesting problems concerning Torelli groups, namely, is the Torelli group finitely presented? So can we find a finite presentation for it with finitely many generators and finitely many relations? And the answer is not known for any G. And of course, this problem is closely related to the problem of is the second homology group finitely generated. This is only one way connection. So if the second homology group is not finitely generated, then the group for sure is not finitely presented. But the opposite implication is not true, but at least this is, well, for no of this question is, the answer is no. And what I'm going to speak now, in fact, I would like to describe a possible approach towards proving that the second homology group of genus 3 Torelli group is not finitely generated. And so the group itself is not finitely presented. It is still open question. I have no proof of this fact, but I have some strong progress towards it. And I would like to describe some things around it. Okay, first of all, I want to mention that, well, these starting, all results starting from this Bestvina books Margalit paper, they were obtained using their result and my results also. They were obtained using the action of Torelli groups on some special, very convenient complex, CW complex, which they constructed in their paper, and they called it the complex of cycles. And also this approach is also based on the action of the Torelli group of, okay, starting from this point, I would like to speak only about genus 3 Torelli group, the action of this group on some special complex of cycles. I will give explicit definition later, but my approach is okay. The complicated thing here is that action of
sorry for interrupting. Are there any generalization towards the case of curves with marked points?
It's a good question. Unfortunately, I do not know any reasonable generalization for marked points. There are good generalizations of Torelli groups to the case of surfaces with boundary components. They are still non-trivial. The matter is that they are due to Putman, and they are non-trivial in the sense that he was first to understand that we need not only surface with several boundary components, but we also want to have partition of the set of these boundary components, and for this data one can define Torelli group of the surface with partition of its boundary components. I do not know reasonable generalizations to the case of punctures.
Sorry.
Okay. Okay, but before, yes, I just would like to say several words that, okay, I would study the action of the Torelli group on complex of cycles, which is known for more than 10 years, so it is not new. But the main difficulty here is that the spectral sequence, there is a spectral sequence for this action which converges to the homology of Torelli groups. But this spectral sequence has many non-trivial differentials. This is a very complicated combinatorial and algebraic object. And I would like to suggest some new approach to studying differentials of this spectral sequence. So the spectral sequence itself is not new. Okay, but before coming to that, I would like to mention one very important for me ingredients, which is also maybe the most beautiful thing related to Torelli group. Till now, I told only about connections of Torelli groups with modular space, with Teichmuller space, and so on. But there is also very nice connection, a relationship with three-dimensional topology, and it is called Bierman-Craig's homomorphisms. I recall that there is a famous theorem by Rayleigh of 1950s that if we have closed spin manifold, then its signature smooth closed spin manifolds, four-dimensional smooth closed spin manifold, then its signature is divisible by 16. Based on this theorem, one can introduce a Rayleigh invariant of three-dimensional homology spheres. Of three-dimensional homology spheres. So if we have a three-dimensional homology sphere, then it is not hard to show that it always is a boundary of a four-dimensional spin manifold, but with boundary, okay, with boundary in 3. So since it is spin manifold with boundary, its signature is not necessarily divisible by 16, but the intersection form is still even, so the signature is always divisible by 8. And one can define Rayleigh invariant to be the signature of this four-dimensional manifold. We should divide it by 8 and then take modulo 2. Indeed, if we have two such spin manifolds, another spin manifold, whose boundary is also M3, then together they form a smooth, closed smooth four-dimensional manifold, and its signature divisible by 16, and so this Rayleigh invariant is well defined. Okay, and now one can produce a homomorphism of Torelli group to Z2 using this Rayleigh homomorphism. Namely, let us consider the standard Hegor splitting of S3, just the very standard one. If we have okay, we can take genus G, standard genus G Hegor splitting. And now if we have an element of the Torelli group, then we can cut along this surface and reglue these two pieces together in a way twisted by this H. So H is just the diffeomorphism from this surface to itself. This is surface of genus G, and we can reglue it back twisted by this element. And then we get a three-dimensional manifold, which is not necessarily a sphere, but since this H is in the Torelli group, so on the level of homology, we have changed nothing. And because of that, it is always a homology sphere. And we can take the Rocklin invariant of it. The Rocklin invariant of this homology three-sphere. And Bierman and Krebs showed that this mapping rho from Torelli group to Z2 is a homomorphism. Okay, so we obtain a homomorphism from the Torelli group to Z2. But in fact, we obtain not one homomorphism, but we obtain plenty of them. The matter is that we can identify our surface, our initial genus G surface, with this particular surface of the Hegor splitting in different ways. The other point of view is that we take this one homomorphism and we act on it by the whole mapping class group. And so we give many homomorphisms from the Torelli group to the two. And actually Johnson showed that these homomorphisms are indexed by so-called SP quadratic functions. On the homology of the surface with coefficients in Z2. Namely, okay, if one has such Hegor splitting, one can always consider the following self-linking form on the homology of the surface. Okay, if he has something like that, some one-dimensional homology class of a surface, then one can push it into one part of Hegor splitting and then into the second part and take the linking number of them modulo 2. And it can be shown that this mapping from homology of the surface to the 2 satisfies the following law for all classes X and Y. And so considering different Hegor splitting, we can obtain different functions omega with this property. But there is also, they are called quadratic functions on the homology of this surface G, of this surface as G. But one more property of it is that for any such quadratic functions, we can consider its ARF invariant. By definition, it's the sum like that, where A1, AG, B1, BG is a symplectic basis. And this is an element in Z2, and it can be shown that this element is independent of the choice of a symplectic basis. And so, and also, again, a not very hard fact that from Higard splitting of a three-dimensional sphere, when we obtain such function omega, the corresponding Arf invariant is always 0. This is a restriction. And okay, namely, these quadratic functions with 0 Arf invariant are exactly those the Bierman-Craig's homomorphisms are indexed by quadratic functions with 0 Arf invariant. So for each quadratic function omega with 0 Arf invariant corresponds a homomorphism of Torelli group to the 2. Okay, once one has such homomorphism, one can easily compute its values. In fact, now maybe it's good time to speak which elements are in the Torelli group. First of all, there are elements like that. We can consider separating curve, a simple closed curve on a surface that separates surface into two parts. And then we can take the then twist about this separating curve. Then twist means that we cut along this curve, twist one of the sides of this curve by the 2 pi and reglue it again. This is called then twist. And if we take then twists about any simple closed curve, then we get elements of the mapping class group. And it is known that mapping class group is generated by such twists. But if the then twist about a curve belongs to the Torelli group if and only if this curve is separated. But these elements are not enough to generate the whole Torelli group. And we have also elements of the second type. Namely, we can consider two homological simple closed curves that separate surface together. And such situation will be called a bounded pair. And then there exists a bounded pair twist, which is just twist about gamma 1 and twist about gamma 2 in inverse direction. Okay, and there is an old theorem by Powell, which was later reproved in an easier manner by Putman, that such elements generate the whole Torelli groups. That this is not such, such elements generate the Torelli group. This is not a good simple, a good finite set of generators. This is just an infinite number of generators, and but still, at least this is useful, very useful result. And
excuse me, may I ask a naive question? what you said is somewhat strange to me, because if we take a separating curve, like in the first drawing,
Yes.
and move it to the whole of the surface, it looks like it degenerates to certain composition of gamma 1 and gamma 2 with no -1 power.
You mean that?
I mean that the curve gamma becomes a pair of curves gamma 1 and gamma 2, which are, so to say, passed in the same direction, not one in...
But okay, the then twist is completely different. This is neither this one nor that one.
Uh-huh.
It is completely different. When the curve, okay, when we take then twist about this curve, any point goes this direction.
Right.
And here, completely different situation. Some points goes just here, and some points go here. It is a different picture. It's completely different elements of Rayleigh groups.
You mean there is no kind of continuity?
No continuity of this.
Yeah. Okay, thank you.
Sasha, sorry.
Yes.
May you be more precise about Powell's theorem? What do you mean by such elements? Are they only bounding pairs or both bounding pairs and standard then twists?
In fact, both. But if genus is at least 3, then only bounding pairs are enough. One can easily show that. I'm not completely sure that Powell did it. Maybe it is later result, but it is easy that if genus is at least 3, then any separating twist can be written as product of bounding pair twists. But if genus is 2, then we have no bounding pair twists at all. We have no possibility to organize a bounding pair inside this surface. So we have vice versa. We have only separating twists.
Okay.
Okay. So we have such some amount, but finite amount of finitely many homomorphisms from Torelli groups to Z2. In fact, Johnson showed that these homomorphisms, first of all, he find all relations between them. There are relations, they are not linearly independent, but all relations between them are known. And in fact, all these homomorphisms generate the whole group, the first group homology. So any homomorphism of the Torelli group to Z2 is a linear combination of this Bierman-Krebs homomorphism. I'm sorry, I started to say about values of these homomorphisms on elements which generate Torelli groups, but I didn't finish. Okay, now suppose that we are given this quadratic function with 0 Rth invariant, and we are interested on value of rho omega on these two types of generators. First of all, let us start with separating curve. If we start with separating curve, then we can consider one half of the surface, and for it we may find a symplectic basis for homology here, A1, B1, and so on. Maybe we have several holes here, AH, BH, where H is the genus of the left part. And the value here is the the value over omega on this twist is the sum of omega of AI, omega of BI. This looks very similar to Arf invariant, but we take the sum not for the whole symplectic basis, but for symplectic basis of one part. And since the Arf invariant of omega is 0, this is independent of which part we take. Okay, and similarly for bounded pair. For bounded pair, we should do like that. We find some separating curve that together with gamma 1 and gamma 2 bounds a 3-punctured sphere. And for this part, we again find symplectic basis of the homology of it. And also let C be the homology class of this of the curves in the bounded pair. And then the answer is as follows: the value of the Bierman-Krebs homomorphism on this bounded pair twist is like that. We should take omega of C plus 1 and multiply it by the same sum. So if omega of C is 1, then we always get 0. But if omega of C is 0, then we may get not 0, but something. Okay, these formulae are due to Johnson also. And one may use this formula to compute Bierman-Krebs homomorphisms for particular elements. What is very surprising that still up to now there is no way to prove that Bierman-Krebs homomorphisms are well defined, avoiding Rocklin's theorem. So we understand that these homomorphisms are well defined since we have this interpretation through 4-dimensional manifolds and Rocklin theory. But then we can compute the values on these generators, but these generators are not independent. There are many relations among them, and these homomorphisms are well defined, and there is no easy group theoretic or combinatorial explanation why, only through Rocklin theory. So it seems to me that it is a very nice situation. Okay, now I would like to go to the action of the Torelli group on this complex of cycles. And first, I would like to recall the general situation. Namely, I would like to recall how one can construct a spectral sequence if some group acts on some contractible CW complex. So the situation is as follows. For a moment, we can forget about Torelli groups, but in a few minutes, I will apply this general construction to Torelli groups. So suppose that some group G, which is discrete group in the sense that it has no topology, just countable group or something like that. So G acts cellularly and without rotations on some contractible CW complex X. Okay, cellular just means that every element of G, any element of G takes every cell of X to a cell again. So it acts preserving cell structure. Without rotations mean the following, that once an element G fixes some cell sigma setwise, so it fixes the cell as a set, it maps it to itself, then it always fixes sigma pointwise. So we assume that there is no difference between stabilizer of a cell as a set and the intersection of stabilizer of every point. Okay.
Excuse me, but in this case, sigma has to fix the neighboring cells.
Okay. Maybe I give one example and it will. Okay, first of all, consider segment and consider Z2 that acts just by reversing this segment. Then this is not without rotations. This is rotation. We fix this segment pointwise, setwise, but not fix it pointwise. Let us add here one extra vertex. Now the same action is without rotation. Since this doesn't. Okay, we can consider, for instance, such situation. The group Z2 acts by this reflection. Then we have here stabilizer of this segment, but it doesn't stabilize these two cells. Okay, so this is without rotations.
Yes, I think it's clear that there are non-trivial elements, sigma, which act without rotations. But if a sigma preserves a cell pointwise, it has to be identity, right?
It has to be identity on this cell.
On this cell and on the complex.
No. Here is an example. This sigma preserves that cell pointwise. But not the total complex.
Yeah. Thank you. Now I understand. Thank you.
Okay, and if we are in this situation, then we can proceed as follows. We can construct a B complex, just B complex of a billion groups. We can take the cellular chain group of EX, and we can, the group G acts on it, so this is G module. This is module over the ring of the group ring of G. And another, we also take the projective resolution. This is an element of projective resolution for Z over ZG. And we can take the tensor product over this group ring, and one get these such bicomplex. And the first differential, we have differential D prime induced by differential of this cellular chain complex, and we have differential D2 prime induced by differential in projective resolution. And now one started from this bicomplex, there is a standard way to construct a spectral sequence. the zero sheet of this spectral sequence is just this bicomplex, and the zeroth differential is just D2 prime. And then one can show that the first sheet admits the following very nice description, namely, well, I write the formula and then explain. Okay, what is written here? We take a p-dimensional cell of the complex, and for it we consider its stabilizer, and so the spectral sequence starts from homologies of stabilizers. And this X, calligraphic X, is just, we should take not all p-dimensional cell, but we should take representatives of all G orbits.
I'm sorry, say again, please. What is this, how to say, beautiful X with subscript P?
It's some set of representatives of all G orbits of the cells. The group acts on the complex, so we should not take all P cells, but we should take exactly one P cell in every orbit.
Okay. Thank you.
Of course, all cells in the same orbit have isomorphic stabilizers, so it is the stabilizers are conjugate to each other, so it is not important which representative to take. So the first sheet of the spectral sequence has such explanation, has such interpretation, such formula, and this spectral sequence converges to the homology of the group. This is standard fact. It is can be found in most handbooks on group homologies, and so the situation converges means that, okay, this is first quadrant spectral sequence, so it lives here. Initially on page E1 we have here some information on stabilizers, and then we have first differential leads in the differentials are like that. So each differential D1, D2, D3, and so on. On each sheet we take the inner natural, as usually we take the kernel of differentials, quotient by the image of the differential to this cell, and this is the next sheet, and we proceed in this way up to infinity, and then on each diagonal we see consecutive quotients on kth diagonal we see kth homology of the group, consecutive quotients of it associated with some filtration in this homology group. So this is usual construction of spectral sequence. And now the most important, I would like to apply it to the action of the Torelli group on some particular complex. And now the most important ingredient is that complex of cycles. Which is due to Bestvina books and Margalit, 2007. the construction goes to for arbitrary G, but I will be interested only in genus 3, so I don't want to speak for arbitrary. Okay, let us consider this genus 3 surface and consider all possible, let C be the set of isotopic classes of all possible oriented simple closed curves, So for instance, like that. Ah, well, non-separated. I forget about this. Non-separated. Only non-separated curves are now interesting to me. And let us fix one for the whole construction, fix a homology class of the surface, and it is convenient to me to fix it primitive, so it is not divisible by, it is non-zero and not divisible by any positive integer. And for each such class, I can consider different cycles for it. I can represent this class, say as some, I can consider several, curves here, gamma 1, gamma 2, gamma 3, gamma 4, and so on, and I can try to write X as some linear combination of the homology classes of gamma i's with some maybe real coefficients. If we write X in such way, then I can consider the linear combinations of the corresponding curves, not of their homology classes, but of the curve itself, and consider this linear combination as an element of such infinite dimensional vector space R to the power C. So vector space with bases corresponding to all possible isotopic classes of oriented simple closed curves. It is even better to consider cone rather than R, since I always want to have all coefficients non-zero. But now suppose that this surface is equipped with a hyperbolic metric. Once a hyperbolic metric is fixed here, one can count the length. Well, this will be cycle, and the length of the cycle is by definition the sum of this by the length of a geodesic representative of a curve, or of an isotopic class of a curve. Once we have a hyperbolic metric, we can consider lengths of all cycles. And so it is a natural task. We can try to choose the shortest cycle that represents X in homology. So one can ask, what is the shortest cycle for X? Okay, the answer definitely depends on the metric, but we can consider in RC, we can consider the subset consisting of all cycles for X that are the shortest for at least one metric. And this is the complex of cycles. So we are interested in all cycles for X that are shortest so that we can find a hyperbolic matrix so that this cycle becomes the shortest one. For instance, it is easy to see that the shortest cycle for X cannot have components with opposite homology classes. It will never be shortest. It is always possible to make both corresponding coefficients smaller. So there are some restrictions. For instance, if the cycle is shortest for at least one hyperbolic metric, then its components are always disjoint, and so on. And actually, this complex can be easily combinatorics can be easily described explicitly. So it is constructed in such maybe implicit way, but then it can be described completely explicitly. But okay, this implicit construction, in fact, one can obtain from it that this complex is homotopy equivalent to the Teichmüller space. Namely, for each point of a Teichmüller space, is exactly the metric. For each of it, we get the shortest, not always one shortest, but some convex cell of shortest paths, and so we get something like not completely a mapping from Teichmüller space to B, but it can be made a mapping. So, in fact, one obtain from this fact, Bestvina and Books and Margalit proved that this complex is contractible. And now the whole mapping class group doesn't act on this complex, since we have fixed one homology class, and this homology class plays important role in the whole construction. But the Torelli group fixes this homology class, and so it acts on this complex of cycles. It is not hard to show that it acts on it cellularly and without rotations, and so one can apply the above general construction of spectral sequence for this situation, and one can consider the spectral sequence for the action of the Torelli group of genus 3 on the corresponding complex of cycles. And okay, I would not like to describe the combinatorics of the complex of cycles in all details, but I just need to say how vertices, edges, and two cells look in dimension for genus 3. First of all, there are vertices like that. Suppose that we have 3 oriented simple closed curves, alpha 1, alpha 2, and alpha 3, so that X is that fixed class, which is fixed throughout the whole construction, so that X is a linear combinations of their homology classes with positive integer coefficients. then I claim that this point n1 alpha 1 plus n2 alpha 2 plus n3 alpha 3, it's a vertex of B3. Indeed, it is easy to find a hyperbolic matrix so that alpha 1, alpha 2, and alpha 3 are very, very short, are almost zero length, but all other curves are not so short. And then, of course, this is the shortest representative for X. If alpha 1, alpha 2, and alpha 3 are sufficiently short. Okay, there are also other vertices, namely, one can consider only two oriented curves, alpha 1 and alpha 2, so that X is their linear combination, and also one can consider only one curve in homology class X itself, and again these are also vertices. It can be shown that these three types are all vertices, but I will be interested only in vertices of this first type. Okay, and also I would like to say something about edges. Again, we have several possibilities for edges, but I am interested only in those edges that contain vertices of this first type, and then not so. There are only few possibilities. Okay, and in fact, there are three main possibilities. First of all, consider the following situation. Suppose that we have four curves that are like that. This is alpha 1, this is alpha 2, this is alpha 3, this is alpha 4, and we have, first of all, X is a linear combinations of alpha 1, alpha 2, and alpha 3 with positive integer coefficients. And second, we see from this picture that alpha 4, its homology class is just the sum of homology classes of alpha 1, alpha 2, and alpha 3. Then we can choose a metric, a hyperbolic metric, so that again, alpha 1, alpha 2, alpha 3, and alpha 4 are very, very short. All other curves are not so short, but also I want that the length of alpha 4 is exactly the sum of the length of the first three curves. I can choose metric in such a way. And then, okay, we can consider, we can consider cycles like that. We can take some coefficient m alpha 4, and then we can take n1 minus m alpha 1 plus n2 minus m alpha 2 plus n3 minus m alpha 3. And all these are one cycles for X. In homology, we always get X. And these are one cycles for X, and all these one cycles have the same length. And so all of them are shortest. And so we see this segment in this complex of cycles. So this is
M is real here, yes?
Well,
M is real.
Yeah. M is real, and M changes so that the only condition is that all coefficients are non-negative. So we get exactly segment. M is from 0 to minimum of Ni. Okay, this is one possibility. It is also possible in similar way to consider okay, instead of taking alpha 4, which is equal to alpha 1 plus alpha 2 plus alpha 3, we can take alpha 4, which is equal to alpha 1 plus alpha 3 2 minus alpha 3 and proceed in a similar way. I don't want to go in details here. We again get a segment, but also we can get a segment of different, a cell of different kind. Namely, we can consider 4 curves like that. Alpha 1, alpha 2, alpha 3, and alpha 4, whose homology class is alpha 1 plus alpha 3, alpha 2. Okay, the same situation, but we just will not, without minus m here, and all the same, all except for this is the same. Okay, this is almost all, but we have one more interesting possibility. We have also one cells which are like that. We can consider, say this would be alpha 1 and this would be alpha 1 prime. They are homologous to each other, alpha 2 and alpha 3. And now we can find a hyperbolic metric so that again these 4 are very short, all others are not so short, and length of alpha 1 is equal to length of alpha 1 prime. Then it is not we get the same length independently of whether we take alpha 1 or alpha 1 prime. And so we again get a segment, since we can take any linear combination of alpha 1 with and alpha 1 prime with non-negative coefficients. Okay, and actually the claim is that these are all types of cells that contain vertex of this first type. And now the main construction. What I want to do, I want to consider the spectral sequence for the action of the Torelli group on this complex of cycles. I am interested, okay, here we have Q and here we have P. In fact, it is not hard to show that the dimension of this complex is just 3. So all the spectral sequence lives in such strip of width from 0 to 3. And in fact, I am interested in this particular cell, in cell with 0, 2. So this cell, the group A1 in this cell, is the sum over all representatives of 0 cells, so all representatives of orbits of vertices. These are orbits of vertices. And here I should take the second homology of stabilizer in Torelli group with integral coefficients. Okay, this is that group. What I'm going to do, I will construct infinitely many homomorphisms from this group to the 2. So that they are linearly independent. If we have infinitely many linearly independent homomorphisms, then we of course understand that our group is not finitely generated. I would like to prove that this group remains not finitely generated after all differentials. We have 3 differentials. We have no differentials from this cell since they all go to 0, so no differentials from it. And we have 3 differentials to it. We have first differential d1, we have second differential from this cell, and we have third differential from that cell. If we could, so I will construct this homomorphism theta I. I will explain how they are constructed. There will be infinitely many of them. If one managed to prove that all these homomorphisms vanish on the images of the differentials, then one would get infinitely many homomorphisms from infinite sheet of the spectral sequence to the 2. And then one would get that this is conjectural. One would get that this group is not finitely generated, but this is this second diagonal of the limit sheet of spectral sequence corresponds to H2, to the second homology of Torelli group, and so it would follow that this is not finitely generated, and hence A3 is not finitely presented. What I know, I can construct these homomorphisms. I think that they look very, that it is very reasonable that in fact they vanish on images of differentials. But in fact, I can prove that all these theta A vanish on images of the first 2 differentials of D1 and D2. For D1, it is more or less from construction. I will give construction for this theta A in a moment, and then I will explain that for D1 it is not so hard. For D2 it is very hard proof, but still I don't know about D3, but I have some feeling that they should vanish on it. Maybe not all of them, but at least I hope that it is possible to find infinitely many linear combinations of these homomorphisms that vanish here, and then will be done. Okay, but now, okay, what is theta A? What is this homomorphism? In fact, each this homomorphism will sit on one of the summons. So they initially then they will be linearly independent, just because they sit on they are supported on different summons in direct sum decomposition. And these summons correspond to such vertices of the complex of cycles. And now consider this vertex. In fact, this letter A stands for I3 orbits of such vertices. And there are infinitely many of them. For instance, since there are infinitely many possibilities for these positive integers, so definitely we have infinitely many orbits. Okay, suppose that we have such three simple closed curves, and I denote this multi-curve consisting of these three curves by M, and I would like to find some homomorphism from the second homology of the stabilizer of this multi-curve. Stabilizer of multi-curve is the same as stabilizer of the vertex of complex of cycles. I would like to construct a homomorphism from here to the 2. And this homomorphism is constructed in the following special way using Bierman-Craig's homomorphisms. First of all, let us consider, let A1, A2, and A3 be the homology classes of these three curves of alpha 1, alpha 2, and alpha 3. And I would like just modulo 2 homology classes. Modulo 2 homology class. I would like to consider quadratic functions from homology of my surface to the 2 with 0 Arf invariant. And now I would like to impose the following condition. I want to consider only those quadratic functions that have value 1 on each of those three classes, A1, A2, and A3. How many quadratic functions with these properties are there? It is easy to see that there are exactly 4 such quadratic functions. Indeed, if we extend this alpha 1, alpha 2, alpha 3 to a symplectic basis, then, okay, the value of quadratic form is, if we give value on each of the element of symplectic basis, then we describe the function completely. Here we must have 1. Here we have 2 possibilities. We can 4 possibilities. We can have zeros on all b's, or we can have 2 1s and 0. So we have such possibilities. Because if we have either 1 unit or 3 units here, then the Arf invariant would be 1. So we have 4 such quadratic functions: omega 0, omega 1, omega 2, and omega 3. And I denote the corresponding Bierman-Craig's homomorphisms by rho 1, rho 2, rho 3, and rho 0. And now I can construct a special 2-dimensional homology class. Just sum over, I take sum over all pairs just of cup products of this rho I and rho j. Indeed, since rho I is a homomorphism from Torelli group to the 2, I can regard it as an element of 1-dimensional cohomology of the Torelli group. And so I can consider such 2-dimensional cohomology class. Okay. The first natural question is, maybe it is, and okay, of course, such cohomology class gives me a homomorphism from this stabilizer to the two. Actually, it gives homomorphism from the whole Torelli group, but I would like to, from the homology of the whole Torelli group, but I would like to consider it only on the stabilizer. Okay, first of all, why it is non-zero? It is non-zero since I can take here two separating curves, delta 1 and delta 2, that are like that. And actually, a direct computation using that I can always I can consider. Okay, I can compute the values of those four functions omega. I have four of them: omega 0, omega 1, omega 2, omega 3, and I can consider the, not of omega, of the corresponding Bierman-Krebs homomorphisms. I can just compute their values on these two twists about these two separated simple closed curves, and for certain numbering of homomorphisms, the result would be as follows. We can number these homomorphisms so that the result of computation is as follows. And then since these two twists commute, they give the so-called abelian cycle in the second homology. For any two commuting elements of the group, corresponds an element of the second homology. It is just the, okay, we can consider the mapping from Z cross Z to our group that takes generators of the summons to these two particular elements, commuting elements, and then the image of we have here the generator of the second homology group, and it goes to the second to an element of second homology group of the Torelli group. And it is easy to compute using this computation that the value of this class, of this homomorphism theta, on that particular homology, element of homology, is non-zero. So these homomorphisms are non-zero. But now, okay, I'm approaching the end of my talk, but now we have these edges which are like that. We have these edges that go from our vertex. We have edges of this type. This is almost the same. We have second type, and we have third type. Okay, for the edges of the first and of the second type, it can be proved more or less directly that the image of those cohomology class theta, if we restrict it to the stabilizer of the edge of either first type, or this is also first, or the second type, if it is edge of first or second type, then we can prove that it is zero. This means that, okay, I would like, okay, this means that when we start from when we study the first differential, and when we start from stabilizers of edges of these first two types, then we always our homomorphisms vanish on the image of this differential. But we also have edges of this third type. Here we again have the same pair of separate and simple closed curves. So here theta on stabilizer of this edge is non-zero. But the matter is that in this case, our edge endpoints of our edge lie in the same orbit. It is not hard to see that there is an element of Torelli group which preserves alpha 2 and alpha 3 and takes alpha 1 to alpha 1 prime. So here we have the same I3 orbit, and when we compute the differential d1 of such element, just we have coefficient 2 corresponding to these two ends, and so modulo 2 it is always 0. Okay, it is more or less explanation why this theta vanishes on the image of the first differential. For the second differential, situations is much more complicated. I am not going to describe it in any details, but I just would like to mention one very interesting thing that appears here. Okay, let us consider the quotient of the complex of cycles over Torelli group. It is still highly non-compact. It is non-compact, it has many, okay, something like that. It's some non-compact three-dimensional CW complex. When I am interested in this cell has number 2, 1. So it corresponds to direct sum of first homologies of two-dimensional cells. Okay, so here we have different two-dimensional cells. For each of them, we have some elements on their first homology, and actually an element here is some complicated linear combinations, a linear combination of something that lives on two-dimensional cells here. And when we want, okay, for instance, here we have some vertex, and we would like vertex is indexed by this letter A, and we have some homomorphism theta A which corresponds to that vertex. And okay, if we take some linear combination, Xi, which lives in this group, and we would like to compute the value of our homomorphism theta on the second differential of this Xi, then of course only some neighborhood of this vertex is important. Everything which is far from it seems to be not important. We can compute this differential in this neighborhood. And then it turned out that there is no local abstraction for this to be non-zero. So if we consider only locally, if we forget about everything which is far from here, then we can construct locally some cycle which seems to give non-zero value. But then we need to extend this local cycle. It is cycle only in the neighborhood of vertex, but we would like to extend it to a global cycle. And it turned out that it is impossible, since the cycles always grow to some non-compact end of our complex. So we have not local obstacle to this, but we have global one. And it is strange, but this growth, there are two different reasons why such non-zero values could exist. And these things grow in two different ways. Namely, in one sense, one can consider, okay, for each vertex here, one can consider each vertex here corresponds to 3 curves, so that X is linear combinations of their homology classes. And as a measure of the complexity, first measure, one can consider the sum of coefficients. And it turns out that if we have this cycle which is going to give us non-zero value, then this cycle should grow so that the sum grows unboundedly. And so, in fact, this cycle has uncompact support, but such cycles are not allowed at all. So we always have zero. But there is another situation in which this cycle grows in different way. It grows in some different direction. Namely, we should consider some linear function from integral homology of our surface to R. And as a measure of complexity of a vertex, we should take something like maximum of f of alpha I. And also for cycles of another type, this value will grow unboundedly, and this is the reason why such cycle cannot exist. So the final result is, the final result theorem is that theta A vanish on images of D1 and D2. So after these two differentials, we have this third sheet of spectral sequence is not finitely generated. But I don't know what happens after the third differential. If it also vanish on the image of it, then the Torelli group is not finitely presented. The strange thing is that, okay, I even do not know whether this differential, this third differential, is non-trivial. In fact, I do not know any non-zero element of this group. I know plenty. I can describe explicitly this group on first sheet, but then we twice take subgroups of it. And I can describe explicitly the group on the second sheet. It is also described. But then I has this second differential from this group, and I should take its kernel. Maybe even its kernel is zero. I do not know any non-zero element. So maybe this third differential even not exist, but unfortunately I cannot prove it. So maybe this is good time to finish. Thank you very much for attention.
Thank you. Is anybody still alive?
Why not?
No, then please ask the rest of the questions. No questions?
Yeah, maybe I can ask a question. Yeah, I understood that the mapping class group is closely related to the Torelli group, and yeah, are any results about the mapping class group, and in particular about the homology of the modular space of curves can be derived from the results about the Torelli group?
Okay. I think the answer is more or less not, and the reason for this is that the Torelli situation is much harder. We are interested in those questions which are obvious for mapping class groups. For mapping class groups, we know that we do not know homology, of course, but we know that all homology groups are finitely generated. We have no problems like that.
I see.
So here we consider those problems which are obvious for the case of class groups.
Yeah, I see. Yeah, thanks.
Well, okay, so maybe it's already time to finish. So let's thank Sasha for very nice and sometimes clear talk. So thank you very much.
Thank you.
Thank you.
Thank you.
Thank you.
Oh, okay. So I think I should finish it. Okay, thank you once more.